All right, hello geometry students. We are doing this lesson on 8-2, which begins on page 316 in print and 316 in Braille. It's just a plain Braille page, and it's titled 8-2 Parallelograms. And it begins with the definition of a parallelogram about 2/3 of the way down the page after the what'll you learn and why is it important. It's on 316, and find where it starts with a parallelogram. So it says a parallelogram is a quadrilateral with two pairs of parallel sides. A symbol for a parallelogram, ABCD, is a little mini parallelogram in print, and then it says capital A, B, C, and D. In Braille, it's going to be a shape indicator and a G, and then you'll have capital A, capital B, capital C, capital D, and that's it. Reads parallelogram A, B, C, D. And there's a parallelogram on the next Braille page, and it says in the paragraph that notice that in that parallelogram, side AB and DC are parallel sides, and then side AD and BC are parallel sides. And so if you turn the Braille page, print users look immediately below that paragraph, you'll see a parallelogram, A, B, C, and D. It's a four-sided figure, a quadrilateral. A is at the top left, B is at the top right, C is at the bottom right, and D is at the bottom left. At the top, A to B has two little arrowheads in the midst of its side. If you go to the non-consecutive side, the side opposite AB, you go to the bottom, you have side DC. It also has two little arrowheads in the midst of the side. And those two arrowheads are parallel indicators. You learned this quite a while back when we talked about parallel lines and transversals. And because there's two on AB and two on DC, it's showing congruency like tick marks. And then on the far left side, AD, there is one parallel indicator, an arrowhead in the midst of it. And the side opposite AD, the non-consecutive side, BC, also has one parallel indicator arrowhead. So 1 to 1, that indicates they're congruent also. So a parallelogram has parallel sides and congruent sides. The parallel sides are congruent. We're going to talk about the different theorems in relationship to parallelograms, and we get to those theorems by using our inductive and deductive reasoning from previous chapters, especially the one where we talked and learned a lot about parallel lines and their transversals, and alternate interior and exterior angles, corresponding angles, and consecutive angles. That kind of information is going to play out here in defining and determining and coming up with the theorems for a parallelogram. So now turn several pages because there's a graphing calculator exploration exercise, and let's get our way to 317A. And print users were in the middle of 317, and we're looking at theorem 8-2. And in words, it says opposite angles of a parallelogram are congruent. So it shows a picture of a parallelogram A, B, C, D. A is in the top left, B is the top right, C is the bottom right, and D is the bottom left. At vertex A, there is a congruent, a tick arc, and the angle opposite is vertex C, and there's a congruent tick arc. So it's showing opposite angles are congruent. At angle B in the top right, there's two tick arcs, and in angle D, there's two tick arcs. And if we just recall, again, parallel lines with transversals, we're creating alternate interior angles and alternate exterior angle situations here. So these angles should be congruent to each other. In symbols down below the drawing, it says the angle A is congruent to angle C and angle B is congruent to angle D. So that's the first theorem for parallelograms, that opposite angles of a parallelogram are congruent. If you turn the page, we get to Theorem 8-3. This should coincide with the last theorem. If opposite angles are congruent, then we're going to have opposite sides be congruent. And this falls in line with what you learned about isosceles triangles. When you had your two legs and they're congruent to each other, the angles opposite those legs were also congruent to each other, those base angles. So in a parallelogram, if you have two angles that are congruent to each other, the sides opposite those angles are also going to be congruent to each other. So, angle A and angle C were congruent to each other. The side opposite angle A is DC, and it has a tick arc through it. The side opposite angle C is AB, and it has a tick mark through it. So AB is congruent to DC. You have the same parallelogram ABCD starting at top left and going clockwise. Now, you know that D and B, those vertexes are opposite and congruent to each other. Therefore, the sides opposite each one of those vertexes are also going to be congruent to each other. So the side opposite D is all the way over and it's BC. It has two tick marks through it. And the side opposite B is all the way over at AD. It has two tick marks through it. So AD is congruent to BC. And down in symbols, underneath your drawing, it says AB is congruent to DC and AD is congruent to BC. The next theorem just shows a plain old parallelogram. It doesn't really give any information. It's more to focus on the words and the symbols. But Theorem 8-4 says that the consecutive angles of a parallelogram are supplementary. So that too you should kick in. Where does that word consecutive come into play? One right after the other. Consecutive angles with parallel lines and a transversal are one right after the other, and they're always supplementary. So here you have sets of parallel lines with transversals. Your consecutive angles are going to be supplementary. So if you started angle A in the top left, the consecutive angle would be B if we went clockwise. A and B added together are going to be 180. You could start at A at the top left and go down to the bottom left, and those are consecutive angles, A and D. They have to equal 180. And then DC would equal 180 and CB would equal 180. Down below, there's some of the symbols. Measure of angle A plus the measure of angle B is 180. The measure of angle A plus the measure of angle D is 180. We could put forth a bunch of different symbols to represent the supplementary relationship of the consecutive angles. So using those theorems, we get to the next example that then leads us to a further theorem. But we learned that quadrilaterals, what is the sum of the interior angles of a quadrilateral? You should hopefully be yelling out learned from lesson 8-1 that it's 360 degrees. The sum of the interior angles of a quadrilateral is 360 degrees. So if we know a parallelogram is going to have two sets of congruent angles, then we know two of them better add up to this. They'll have the same two of them will have the same measure, and two of them will have the same measure, or two consecutive ones will add up to 180 each, and 180 is 360. And so let's go through this example, and it kind of has goes through three different proofs to get us to a point of showing that a parallelogram, can have 360 degrees and that sides and angles are congruent. But we're given in parallelogram PQRS that PQ is 20, QR is 15, and S is 70. So we could figure out all the missing stuff about this parallelogram just knowing that information and using our theorems. We have a parallelogram. P is bottom left, Q is bottom right, R is top right, and S is top left. At vertex S, they're telling us that that is 70 degrees. So what do you know about what Q is if you know S is 70? You should know that Q is 70 because opposite angles of a parallelogram are going to be congruent. What do you know about R? Well, R is 110 because you know that consecutive angles are supplementary. So S plus R has to equal 180. So R has to be 110. And if you know that R is 110, what is P? Better be 110 because it's the opposite to R and those are congruent. So now we just figured out all the angles just knowing 1, 70, 70, 110, and 110. Then our sides, because we're told this is a parallelogram, PQ is 20. So the side opposite is SR. What is that? 20. Because in a parallelogram, opposite sides are congruent. RQ is 15. What is the side opposite? SP, 15. So now we know all the angles and all the sides just based upon the information that they said it's parallelogram, and here's your two sides and an angle. And using all our theorems, we're able to prove and deduce out all the other measurements. So then if you turn the page, they give you a your turn on, did I do it yet? Your turn. Okay, we got page 318. They actually have an PSRQ, another one, and they say find the measure of angle Q, but we already did. We did the next three by just talking our way through that one parallelogram. So turn 2 pages, let's see, yeah, 2 pages to 318A. It's just a plain Braille page. It says your turn down at the bottom. There's no drawing, there's just information that we can do the same thing. We can figure out the measurements of the missing sides and angles. So it says in parallelogram DEFG, DE equals 70, EF equals 45, and the measure of angle G equals 68. What are the missing sides and angles? Well, the sides, let's do that very quickly. One side is 70, one side is 45. What are the other two sides? Hopefully you're yelling out 70 and 45 by definition of a parallelogram, and that opposite sides are congruent. And then the measure of angle G is 68. So the angle opposite that is going to be what? 68. The consecutive angle to the angle G, which would be either angle F or angle D, would be 180 minus 68, so it would be 112. And the angle opposite that would be congruent, which is 112. So just using some basic math and your knowledge and theorems of parallelograms, you're able to figure out all the missing sides and angles, only given two sides and one angle. There's two more theorems in this section. The next page, Braille page 318b, has theorem 8-5. It's going to talk about diagonals of a parallelogram. We discussed diagonals of quadrilaterals in 8-1. Diagonals join non-consecutive vertices, non-consecutive angles. What's really cool about diagonals of a parallelogram is that they bisect each other. So tap into your knowledge about what bisect means from a long time ago. Bisect means to divide equally in half. So the theorem 8-5 is saying diagonals of a parallelogram bisect each other. So you know that when you have diagonals, they're cutting each other exactly in half. So this drawing, ABCD, parallelogram ABCD, A is top left, B is top right, C is bottom right, and D is bottom left. There's two diagonals, one going from top left to bottom right, AC, going through point E, and then DB or BD, the other side, the other two pairs of non-consecutive angles. We have another BD or DB. Notice the tick marks. From A to E is one tick mark, and from E to C is one tick mark. It's showing that they're bisecting each other immediately in half. DB, from D to E is two tick marks, and from E to B is two tick marks. So if I told you that AC is 20, you could tell me the measurements of AE and EC. You'd tell me it's 10 each. If I told you BD is 24, you could tell me that DE is 12 and EB is 12. If I told you 1/2 of one of them, you would be able to tell me the length of the whole one. If I told you AE is 5, you would tell me that AC, the complete AC, is 10. If I told you DE was 7, you would tell me that DB is 14. So be very careful paying attention to whether they tell you the full length of the diagonal and you want to split it in half, or they tell you half of the diagonal and you got to double it to find the full length of the diagonal. So that's what they have you do in the next example. if you turn to page 318C, we have example 4. It says in parallelogram ABCD, if AC equals 56, find AE. So you have bottom left vertex is A, top left is B, top right is C, and bottom right is D. And there's diagonals going from each opposite vertex. So from B to D is a diagonal, and from A to C is a diagonal. And then they intersect at a point in the middle because two lines or line segments intersect at exactly one point. So they bisect each other because we're given that this is a parallelogram, so we know that they're being split in half. And you're told that AC is 56. What is AE? So you go from A to C of the entire diagonal is 56. What is it from A to E? So you should be dividing 56 by 2 and saying AE is 28 by definition of a bisector, and by theorem 8-5 saying that diagonals of a parallelogram bisect each other. In the your turn, they ask you if DE is 11, what is DB? So D to E is 11. Now they're giving you part of your diagonal. They want to know the entire diagonal D to B by definition of bisector and by the theorem for parallelograms that diagonals bisect each other. If DE is 11, then you're able to say DB is 22. So pretty basic, just being very careful to realize have they given you the entire diagonal or part of it. Then turn the page. There's a page break and it starts on 319 and it takes us through a proof to get us to theorem 8-6. So let's really walk our way through this. This is really good practice of deducing, of writing that proof so that we can make a conjecture, we can make a statement, a theorem that we accept as true. So it begins with a look back and reminding you that alternate interior angles from less than 4-2 and angle side angle from less than 5-6 are going to come into play here. So alternate interior angles of parallel lines with a transversal are congruent. And angle side angle, ASA, means that an angle, the included side, and another angle of a triangle, that means our triangles are going to be similar. So it says a diagonal separates a parallelogram into two triangles. You can use the properties of parallel lines to find the relationship between the two triangles. Consider parallelogram ABCD with diagonal AC. So they give us a drawing with some marks. A is top left, B is top right, C is bottom right, and D is bottom left. So there's the outline of our parallelogram. You're given that it's a parallelogram in writing, that shape indicator G in Braille and the little parallelogram shape in print. So your brain should be turning on. They've given me a parallelogram in writing, so I know that there's different theorems in regards to a parallelogram that I can tap into. From the vertex opposite each other, AC, they've drawn a diagonal, and notice they've created two triangles. At vertex A, there's one tick mark above the diagonal and two tick marks below it. At vertex C, there's one tick mark below the diagonal and two tick marks above it. Your brain should kick in and realize that that top side AB and the bottom side DC, those are parallel to each other, and this diagonal is a transversal. So this transversal has created alternate interior angles at A and C, hasn't it? BAC is the top side, is congruent with DCA on the bottom side, alternate interior, and then DAC up at the top but on the bottom of the transversal has two tick marks and is congruent to ACB, which is down at vertex C on the top of your transversal. Those are alternate interior angles and they're congruent. So they're putting congruency marks on our drawing. So if we go to the proof, there's some interesting stuff to be reading here with this proof, and some Braille also. So first, number one, they say that DC is parallel to AB and AD is parallel to BC. A parallel indicator would be EDL. And that is by definition of a parallelogram. Parallel sides, opposites. Number two, we state that angle ACD is congruent to angle CAB, and angle CAD is congruent to angle ACB because if two parallel lines are cut by a transversal, alternate interior angles are congruent. And we just write that out. And we talked about that just a few moments ago, that diagonal is a transversal to the top and bottom sides, creating those alternate interior angles. In number three, it says line segment AC is congruent to AC because of reflexive property. So that diagonal is congruent to itself. One way or the other, it's still congruent to itself. So it's reminding us that that diagonal, it's the same for each triangle. It's going to be equal to itself. That's kind of a no-brainer, but we like to write that out in math and remind ourselves that AC applies itself to both triangles, therefore it's congruent to itself. Therefore, angle or triangle ACD, so the bottom triangle, is congruent to the top triangle CAB by angle side angle, because we've got two angles that are congruent to each other in each triangle, and then the side that they share, that diagonal, is congruent to itself. So that included side of the angle side angle, we are able to say that these two triangles are congruent to each other. So we just proved that when you draw a triangle, a diagonal, excuse me, through a parallelogram, you create two triangles and two congruent triangles. Always, always, always. So that's the next theorem. The last theorem for this section is on the next Braille page 319b. It says a diagonal of a parallelogram separates it into two congruent triangles. And it just gives you a drawing. A top left vertex, B top right, C bottom right, D bottom left. That's the outline of your parallelogram. And then they draw a diagonal from A to C, the two opposite vertexes. And down below in symbols, they remind you in symbols that triangle, shape indicator, ACD, so shape indicator T, and then ACD is congruent to triangle CAB. So the bottom triangle ACD is congruent to triangle CAB. And notice how we write them with their corresponding sides. So ACD, we're going to start with C because that angle at C on the next triangle corresponds with the A on the last one. And we're going to go C to A and then to B, CAB. All right? So be careful how you write those. That'll get you into trouble if you don't really think about making sure. Remember, several chapters ago we practiced corresponding angles to corresponding angles, corresponding sides to corresponding sides, always keeping them in order so that they show similarity or congruency. So that's the end of 8-2 on parallelograms. If you want to do some extra practice, it's highly recommended. At least do check your understanding 1 through 9. One of them asks you to draw a parallelogram with the diagonals and name 4 pairs of congruent segments. You could just explain what that would look like. But doing 1 through 9 will help you get through the material that you just learned in this section. And then be prepared in class to do a little review to find missing sides and missing angles, to apply the diagonal bisector theorem of parallelograms, to indicate which triangles are similar or congruent to each other. And then there's a quiz that follows this section. So that's all for 8-2, parallelograms. Do good thinking, and I'll see you in the next video.